다음은 그 리서치 쪽 담당하고 연구 쪽 담당하고 있는 저희 비드에서도 발표를 했었던 알리스테어 스튜어트 소개하겠습니다. Adrian? 죄송합니다. 그 리드 개발자인 그 Adrian을 소개하겠습니다. 네, 박수 부탁드리겠습니다.
Could you switch my slides? Yes, hello. Nice to meet you. Nice to meet you all. So while we're just switching slides, I'm actually going to keep this fairly brief. We've all had 2 days of or most of us had 2 days of conference behind us. We'll have another 2 amazing speakers coming up. I will very briefly sort of give you an intuition for what parachains are, why they may be useful to you, and so sort of what is the difference to traditional smart contracts. So this is by no means sort of a talk to chill parachains as the godsend gift, and then like everyone that ever wants to build any sort of dApps should always use parachains. This is more, there are certain classes of use cases that lend themselves better to parachains than to smart contracts. And I think over sort of the last 2-3 years, we've seen that smart contracts really solve some problems, but they by no means solve all problems, right? There are large classes of use cases which aren't addressed by smart contracts at all. So like anything complex, effectively. Wait, give me 1 sec. Just plug it back.
Yeah.
Yes, sorry about this. As always, technology does not work that great. Yeah, it's on the Google, it's on the right. It's nothing really. This happens, it's okay. We'll be back in like 2 minutes. Anyway, so I haven't given my talk yet, but if you already have questions about Polkadot, we can start with that. Because for that, we don't need slides, or parachains, or anything else about the ecosystem. Okay. God damn it. Can you start? Got it? Yes. Sweet. All right. Thank you very much, guys. And we're back. This isn't the first slide, though. No. Okay, so today I'll talk about smart contracts, parachains, and independent blockchains, sort of the 3 major deployment options you have if you want to build decentralized applications. So you want to build a dApp, right? Like over the last couple of years, everyone has sort of started asking themselves, oh, this new space looks cool, let's look into building dApps. And so traditionally what people did was they built traditionally they did the last thing, independent blockchains, which I'll talk about last, but so in the last 2 years, people, well, let's build a DEX, so let's write a bunch of facility code and sort of try and deploy this to the global network and hope that it doesn't break. This sort of worked very well in the beginning, right? So smart contracts offer you a lot of cool features. They allow you to deploy applications that run forever, that have the ability to interoperate with other applications, right? I, as a smart contract, can call into another smart contract, so you can build these very composable applications. And by now, they're extremely easy to deploy, actually, right? So over the last 2 years, we've built a lot of tooling that makes smart contracts extremely easy to deploy, and like the basic example for this is Truffle. Then, now the sort of new thesis is that parachains solve a lot of the problems that smart contracts already have without sort of giving up on all the benefits. So what parachains are? Parachains are effectively sort of, you can almost think about them like a smart, not like a smart contract, but like a class in Java that implements a specific interface, right? So a parachain is a blob of WebAssembly binary that implements a specific function interface that the Polkadot runtime environment in this case calls into. So there's, for example, a function execute block. And so a parachain really is any piece of code that implements this execute block function and that the Polkadot runtime environment can call into. The nice thing about parachains is that they give you much more flexibility. So in Solidity, people have always talked about, oh, we'd like to implement ZK snarks, but, well, we don't have the right cryptographic primitives, right? Let's try a protocol upgrade. In parachains, you don't have this problem. And parachains are written in Go, Rust, or C++, or any language that compiles down to WebAssembly. And instead of you having to rely on the sort of primitives given to you by the virtual machine, you can almost build all primitives yourself because WebAssembly is much faster to execute. So in case you want some new cryptography, you want to test some cutting edge cryptography, parachains sort of allow you this. So you're not bound to the EVM. You have a much larger tool set available to you as a developer in order to build your decentralized application. Which sort of leads to the next point that you can do much fancier things all of a sudden. Right, that's sort of the primer on parachains. Now we'll go a little bit more into depth on this. And then sort of the last other choice if you want to build a dApp is independent blockchains. And this is sort of how, until Ethereum, most people deployed blockchains. They were like, cool, we want to have a cool new idea. Let's fork Bitcoin and let's sort of hack around in the C++ code base and redeploy that code base in order to have our functionality, right? So this is how Zcash got started. This is not how Monero got started, but so like Zcash I think is sort of the best example of someone that forked Bitcoin in order to add new cryptography to it, in order to add new functionality to their user base. The problem with that approach is that this is extremely difficult, right? You have to sort of hack around an existing legacy code base that really wasn't built for the purpose of extensibility and to allow you to add new functionality. And so I'm not going to talk about this today in depth, but what Parachain is developing is also a tool set called Substrate, which sort of helps you with both developing parachains, but also helps you with deploying independent blockchains. So a blockchain developed with, you can think of Substrate as a set of really useful tools that you can use to deploy your own chains. And those chains can either be parachains or independent blockchains. Yes, so since this is quite important that sort of for parachains and because parachains are sort of a new paradigm, I quickly want to talk you through how the Polkadot architecture actually works. We all know that this diagram isn't like the most clear thing, so I'll try to sort of like gloss over a lot of the details and make it a little bit clearer by explaining what's actually happening. We're looking into greatly simplifying this as well. So, what is Polkadot? Well, Polkadot, and by the way, this is important because parachains live within a Polkadot context. So we have a relay chain, and this is sort of a very simple proof-of-stake blockchain that has two main functions, or actually, I guess 3 main functions. It has governance, it has a proof-of-stake mechanism, and it has the ability to deploy parachains to it. So, and sort of these are the guys here in the middle, and they're sort of just chugging along, allowing other people to deploy parachains to them. So now let's say I've developed some, actually let's say I'm now going to port Zcash as a parachain, right? Because this is something that's potentially actually very interesting. So I've used Substrate to write my Zcash-like parachain, and now I'm ready to deploy it. Well, the process of deploying a parachain is sort of, I talk to these guys, so I talk to the relay chain validators, and I sort of pass a governance proposal to add a new parachain. And the reason why, actually, so this is another important difference between parachains and smart contracts. Smart contracts are sort of deployed in a very permissionless way. Anyone can just like write a silly smart contract and deploy it. This comes at the massive downside that smart contracts have to be metered, right? You have to pay gas, which is like a massive problem from the usability side. Parachains, on the other hand, are unmetered state transition functions. So due to that, though, it means that not everyone can like whip up a bunch of Rust code and deploy Parachain to Polkadot. Instead, you sort of have to prove, like you have to have something reasonable and then talk to the token holder governance and to deploy that Parachain. But as the advantage you get that you don't have to worry about gas metering, at least within deploying this Parachain. So now we have a Zcash-like Parachain. So we have a blob of WASM, of compiled WASM code, and we deploy this to the relay chain validators. These relay chain validators, from, let's say we have 100 here, and we take a subset of those and assign them to validate this parachain. And this is the Zcash parachain. And so every once in a while, this set also changes. I won't go into specifics here. But then on the parachain side, you have a couple of very important functions. And so also gloss over fishermen. Fishermen are sort of combined with collators. So now you have a parachain. But this parachain, the relay chain validators aren't running the entire parachain. So these relay chain validators aren't running hundreds of different blockchains. They're sort of only verifying state execution and then finalizing those parachain blocks. So instead, we have collators. And you can think of collators sort of like traditional full nodes in Ethereum. So if I'm a user of this parachain and I want to submit a transaction, I submit it to a collator. I don't submit it directly to the relay chain validators. And so these collators then gather a bunch of transactions, they talk to each other, they relay transaction between each other. And then one of them assemble a block and they sort of provide a proof of validity of that block to the relay chain validators that then verify this proof and include it in the relay chain. So these collators are really sort of full nodes. The collators also have another important function where if one of the other collators starts lying about the state transitions that are happening, they can at the same time sort of flag this up to the relay chain validators to get someone slashed. This is just normal slashing behavior. Right, this is sort of how parachains work, very briefly. You also see like these other parachains hanging on the side. You can also build, there can be many parachains, but you can also build parachains that sort of allow you to talk to, let's say, Ethereum. So you can imagine it as sort of like a wrapper around an Ethereum blockchain or around the proof of work blockchain, a non-deterministic finality blockchain that allows you to do message passing between these chains. Because this is the other important point, right? Remember how I mentioned in the beginning that the cool feature of smart contracts was that I could call into some other smart contract to gain some functionality from them. Well, you have the same thing in parachain, so that one parachain can sort of call another parachain. And it's effectively asynchronous smart contract calls. It allows you to do things like transferring tokens between parachains, but it also allows you to invoke functionality on other parachains. But for that, we need finality for some more technical reasons. And so these parachains, they get finality provided by the relay chain. But if we want to talk to a non-finality-based chain, we write a wrapper around this non-finality-based chain, and now we can do fancy message passing between those. Yes, so this is very brief, high-level overview of how Polkadot works. We will be simplifying this going forward. So just to sort of recap on the smart contract side, so this is usually written in Solidity, Viper, Michelson. It's like there are all these new VMs coming up. The execution is metered, which has its good sides and bad sides. So good sides are, so if you have it fully permissionless, but the bad sides are that users suddenly have to deal with gas. You have to deal with gas cost. They allow you to do synchronous calls between different smart contracts and are permissionless to deploy. One of the bad sides actually is they are guaranteed to live and run forever, which means that you sort of get this infinite state bloat of things that we aren't actually using anymore. And actually one of the important things is probably one of the best features of smart contracts, which is also shared by Parachains actually, is that they derive the security from the backing consensus system, right? If I'm deploying a smart contract, I don't have to worry about who will secure the smart contract. I sort of send this off into the ether, into the world, and the Ethereum miners will secure the smart contract. And it's an extremely powerful feature, right? You could imagine that Facebook tomorrow could deploy their own currency. And it could be a fully permissionless system, right? They could just write a bunch of facilities code that they don't have any more upgradability control over, deploy to Ethereum, and at that time, like, we have a provable guarantee that these people can't change, sort of inflate, do an arbitrary inflation of the token balances. So it sort of allows anyone to deploy a permissionless system, which is powerful because they don't have to worry about bootstrapping their own security. Then we have parachains. So yeah, as I said, parachains are sort of written in Rust, C++, or Go. I'm assuming that as time goes on, more and more languages will have WebAssembly as compile targets. I bet at some point JavaScript will be compilable to WebAssembly as well. Whether we want that or not is a different question. We have asynchronous calls between these parachains, and we have an execution that is unmetered, so we have no notion of gas, which is really quite nice. And so this point about it allows you to do complex state transition functions is really the fact that you can, since execution of WASM is near native speed, even in the VM, we can have extremely complex state transition functions, which allows you to test out new cryptography. So deployment to Polkadot is actually permissioned by governance, and this is the best part about Parachains. Parachains derive their underlying security model from Polkadot. So again, if I don't want to deploy Parachain, I don't have to worry about finding a new validator set that will secure my state transition function. I rather say, here's this cool application I built, do you guys want to run it? And if they say yes, then they will run it and secure it for you. Which sort of is very nice from a developer's perspective, because instead of you having to worry about both the development and the security of your network, I can rather focus on 99% of my time on the security of on the development of my application. And then the security is sort of offloaded to someone that's doing this all the time. Right, and then we also have independent blockchains. And so when you think about this as sort of a spectrum, independent smart contract, parachains, independent blockchains give you sort of the most so it's a spectrum of flexibility. So you're most locked in on the smart contract side, and then you sort of have a lot more freedom on the parachain side. But if you want ultimate freedom, then you have to go for sort of the independent blockchain side. But freedom comes at a cost. So they can be written in any language, and you have complete complete flexibility in technical choices. They may have synchronous or asynchronous communication with other blockchains. Execution, again, is unmetered, but like the major downside is they have to derive the security from some validator set, so they sort of don't inherit the Polkadot validator set. Which is actually sort of important, right? Like, if we go with this notion that over time, not everything will be a smart contract, but rather we'll have many sort of different state transition functions, different decentralized applications being deployed. If we all do this as independent blockchains, the downside is that we have much weaker security guarantees for each individual chain. Whereas with parachains, we can have one global security guarantee that applies to all parachains at the same time, and these parachains aren't competing for security. But there are some use cases where you want independent blockchains. If you're a very specific community that wants to have full technical control over what they're doing, then this is also a great choice. And the nice thing is you can sort of reuse, Substrate allows you to build both parachains and independent blockchains. Yes, and this is effectively, I'm now coming towards the end of my talk, just some use cases and examples to summarize. So for some smart contracts, it's really something, the use cases where you have something that's extremely cheap on the computationally. So you can't have complex state transition functions. But the nice thing is you can enforce invariance in perpetuity. And in my mind, actually, the best example of why you would want to use a smart contract is because you actually want to have a contract. So not something that not something where I try to execute trades or order matching in a smart contract. That seems like a terrible use case of smart contracts. but rather sort of the final settlement layer, so the arbitrator over some agreement that two parties have. Yeah, so like binding contracts, multi-sig wallets, those are some like nice use cases. Parachains, very complex state, you can have very complex state transition functions, high value applications that require shared security, and due to the design of Polkadot, you also have actually very high throughput on these parachains. So a cool thing for parachains could be DEXs. So it's impossible to effectively build a useful DEX in smart contracts, but it's definitely possible to build an extremely performant DEX within a parachain. E-money zones, and so e-money zones are really these fiat to crypto. Let's imagine something like Tether, where some centralized entity wants to take deposits and issue tokens into the parachain, into the Polkadot ecosystem. They may not want to have to figure out how to run their own validator set, but rather want to use the shared security. And then you have sort of independent blockchains on the side. Many of the use cases of independent blockchains and parachains really overlap. And it really becomes a question on whether you want to have extremely fast communication between different parachains and the fact that whether you want to have shared security. Yeah, so for example, something you can't do in a parachain is you can't sort of pick your own consensus instances. You can't, if you want to have a very specific consensus securing your system, you can't do this in a parachain. So this consensus mechanism is given by Polkadot. Yes, so that's pretty much it from my side. Short and sweet. Do you have any questions about any of what I just said? Oh, yeah.
So is the Parachain just basically a side chain?
Sort of depends on the definition of what a sidechain is. It's not a sidechain. It's its own thing. It's something that has a shared security, that shares the security from the Polkadot validator set. Yeah, I don't know. Do you guys have a?
So I would, maybe I can take the mic from the live stream. Right. Oh yeah, right. So a sidechain is, it's like its own blockchain that has its own security. It runs on its own. It's got its own consensus mechanism. And then you have these two chains, the main chain and the side chain, that sort of can interpret each other's block headers, state transitions, finality, but their security isn't interlinked. Whereas parachains are slightly different. We still have this property that block headers, essentially, of parachains are included in the relay chain, and the relay chain may understand how to interpret the state transitions of those chains, but the security also flows from the relay chain to the parachain. So it's not a separate thing as it would be if it were a side chain. Now, if you have bridges, like bridge parachains, if, for example, we bridge Ethereum to Polkadot, then Ethereum becomes a side chain in that sense. So we have a virtual parachain that enables a side chain. So the bridge is secured by Polkadot, whereas Ethereum is not. So in some sense, parachains sort of encompass the ability to create side chains, but also to create fully chains which are fully secured by Polkadot. So shared security residence shares the validators.
Yeah, so the validators, the validators are shared among all parachains. It shares the economic security guarantees. So all parachains have the same economic security guarantees, whereas if you sort of have independent chains, they each have their own economic security guarantee. Yeah. Yeah.
Yeah, I had a question. You keep saying security, security, security. Do you really mean consensus and finality? Because security has a very broad meaning in computer science, right?
Consensus and finality. Yeah.
Okay, got it. Thank you very much.
Yeah, I was going to ask you to expand a little bit more about state on those bridge chains that you guys talked about.
So it varies from chain to chain because essentially what a bridge chain is doing is it's interpreting the finality of some remote chain. So the state largely relates to that you have headers, recent headers, and then you have proofs of their finality in the bridge chain state. And you may also have, for example, coming from Ethereum, for example, you have log events coming out of smart contracts that actually are meant to indicate messages that are to be ferried across to Polkadot. So you would have a header, a proof of finality, and some kind of Merkle proof perhaps showing that a log event was actually issued that should lead to a message being created on the Polkadot chain.
Any other questions?
So he says as a he evaluates this as a very innovative approach and idea, but he's wondering if such like the branches, will there be an interference between such like branches or yeah exactly. He's wondering if would be any interference.
I can take it. So the question is if there's interference between parachains. So largely no. Parachains, at least from the perspective of a peer-to-peer network, are actually isolated. So they have their own sub-networks where nodes are communicating. Validators have to be partitioned across the parachains. So for example, if you have 100 validators and 5 parachains, at any time 20 validators are partitioned to each parachain. So there is interference in the sense that the security providing resources, the stake of the validators is in some sense distributed across parachains. So you would have, maybe if you had some parachain that was more important than another, then the less important parachain is getting, in some sense, a disproportionate amount of security resources. But I think that's the only instance of conflict that I could really think of.
So another instance of conflict, I guess, could be due to message passing between chains, right? Like Parachain A can sort of send a message to Parachain B, so on Parachain B you actually have to either be able to interpret the entire possible set of incoming messages, or be very restrictive on what you can actually accept. So there will be some amount of complexity that you have to think about especially when you want to interact between parachains. Cool. Thanks. Yeah.
So for a parachain that has a probabilistic finality, like Ethereum, right? Today, we all know between like 6 to 10 blocks, there's still a chance of a reward. How do you handle a reward if that is already went through the bridge and you guys do proof of stake, and like how do you roll it back?
So the parachains themselves don't have probabilistic finality, but if something like Ethereum, like for example, if we transfer a message out of Ethereum or out of Bitcoin into Polkadot, and then all of a sudden Ethereum or Bitcoin is 51% attacked, what do you do?
Well, yeah, today, yeah, the reward.
Oh yeah, so sure, let's I guess reorgs are possible within some bound, although assuming that the chain isn't being 51% attacked and some synchronicity assumption on the network, they're really, really unlikely past a certain point. So the bridge would always basically be waiting that amount of time that under normal conditions, that chain wouldn't be likely to be attacked. However, if the chain were to be attacked and you did have a large reorg, there still has to be some kind of mitigation mechanism.
Like today,
So-
within 6 blocks, it happens all the time.
So
yeah, within 6 blocks. So what if you wait 50 blocks? What if you wait 120? That's what exchanges are waiting.
It's not real time then.
Well, it's not instant, no. And this is something that you could deal with, for example, by having absolute finality, like a deterministic consensus protocol, something like Casper FFG, for example, in Ethereum. but even so, like this is generally a problem of bridged chains, is that you have to account for the fact that they may reorg if they're on probabilistic consensus, or the fact that they may be attacked, which is why you probably wouldn't bridge chains that don't themselves have very high degrees of security attached to their consensus protocols.
So also, like the notion is that, so this isn't fully spec'd out, right? Like this sort of depends on the implementation side of the bridge chains. But the way you can think of is that validators have to sort of set a localized threshold on when they consider a block to be irrevertible on the proof of work chain, right? So like if I'm running a validator, I may say I believe that Ethereum will never reorg after 60 blocks. If you're running a validator, you may say after 600 blocks. And only if more than 2/3 of the economic of the stake in the system actually agree on that this block will never get reorged, then it becomes finalist, and then we can do message passing. And in most designs that sort of I thought about is that if a reorg actually ever happens, you have a large slashing event, where so that validators have an incentive to actually be fairly certain that those will never get reorged. But yeah, so this becomes a problem if, for example, we have a reorg after 1,000 blocks in Ethereum, all of a sudden we have to, it's probably impossible to roll backs, but yeah. It's like an open design space there.
There is a way to design a bridge where basically finality relates to usually a specific fork choice rule, but if you would just have a bridge relay all chain heads and that the dApps would try to interpret finality on their own and message passing, you would basically say, okay, here are all the chain heads of Ethereum, even if there's a 1,000 block reorg, disregarding finality entirely, then you have to do it entirely on the application side. But you're always going to run that risk that if you take some means of finality as truth, that it could be reverted.
Thank you.
So can you talk a little bit about the performance of some of the dApps written on top of this? If they're using a bridge, for example, have you anything tested?
Specifically with bridges, is your question about bridges specifically?
Say for example, I want to build something maybe DEX related on and using Polkadot, the bridge on a certain network. How have you guys had any cases where you can measure it, see how performant it is?
So I would venture to say that if you, for example, if you build, one of the goals of Parachains is specialization. So that means that you can do specific kinds of computation very quickly. So Parachains are likely to be specialized. Whereas it's very likely that any chain that's being bridged to Polkadot is general purpose. So the throughput is probably limited by that external chain as well as latency to finality of the external chain. Concrete numbers, I couldn't really say. We have done tests of, like for example, on Ethereum proof of authority networks with parity, we saw in the thousands of transactions per second. We have bridges between such networks. I think it's very likely that if you have specialized substrate chains that they could go at least a constant factor higher.
Yeah, so also an important, for example, for the specific DEX example is that, so the latency between sort of like, let's say Ethereum and your DEX deployed on Polkadot will be high, right? Because we have to wait for the finality guarantees around Ethereum to kick in. But those transactions don't have to happen frequently. So I, as a user, let's say I have like 5 ETH, I move my 5 ETH, and I wait like, say 5 minutes, 30 minutes, doesn't matter. And at that point, we don't have to wait for every transaction 30 minutes. Rather, we can have like latencies in the order of seconds, right? So like if I'm a user, I now have an account on the DEX Parachain, and I want to trade, and I can trade in maybe like 1 or 2 second intervals. And then when I want to go back to Ethereum, this is actually extremely fast at the same time. So going back to Ethereum may only take another couple of seconds. So what we expect is that most users will sort of do this transition from the non-finality systems to Polkadot once, and then mostly will stay within the Polkadot ecosystem and not leave, unless there are like specific reasons why you would want to exit back into the original non-finality chains. Yeah. Any last question?
Yeah, why don't we move on to
Yeah.
Alistair to talk a bit about consensus and finality? It seems to be
Yes.
a recurring theme in the questions.
There you go.